You've got aircraft design, shipbuilding, 3D printing. I mean, on the surface, they seem like they're from totally different worlds, right? But what if I told you they all share this powerful, kind of invisible connection? Today, we're going to pull back the curtain on the one piece of tech that's changing how we build, well, pretty much everything.
Okay, so you look at this stuff and yeah, it's just a wall of jargon, isn't it? Entrained flow gasification, thermodynamic analysis. It's super complex, super technical, and honestly, it sounds like something happening in a lab on the other side of the world, totally disconnected from our lives.
So, the big question is, what does any of this actually mean? What are engineers really doing with these complicated methods?
And maybe more importantly, what on earth does it have to do with your life? You know, the car you drive, the plane you fly in, the stuff you use every day. Well, that's what we're going to do. We're going to connect these super abstract ideas to the real world and show you how this invisible engineering is making everything lighter, faster, and safer for all of us.
All right, so first up, let's talk about one of the biggest challenges in all of engineering. It's this constant battle, this tug-of-war between strength and weight.
I mean, how do you make a part as light as you possibly can without it breaking? Think about it. Weight is the enemy of efficiency. In an airplane, every extra pound costs fuel. But strength, that's totally non-negotiable. It's about safety. So where is that sweet spot? How do you find that perfect balance?
Well, for a long time, the answer was basically brute force. The old way was just to over-engineer it. You know, make it way heavier than it needs to be, just to be on the safe side. But the new way, it's so much smarter. Now, engineers use this incredible software to simulate everything. They can digitally carve away every single ounce of material that isn't absolutely critical for strength. It's precise, it's efficient, and it's a total game changer.
And this amazing technique has a name. It's called topology optimization. The best way to think about it is like this. You give a computer a block of digital clay and a bunch of rules. You say, okay, here are all the forces this part is going to face. Now you figure out the absolute strongest, lightest possible shape. And the results? They're often these wild, almost organic-looking structures that a human would never think of. They look kind of alien, but they are perfectly engineered for the job. And this isn't just a cool science project. The real-world impact is massive. We're talking about more fuel-efficient airplanes because they're optimizing things like the fuselage and the wing ribs. We're talking about lighter, stronger car parts like your tire rims. It's even used to predict how long a part like a crankshaft will last, which makes our machines way more reliable.
Okay, so that's solid parts. But what if the problem is something you can't even see? I'm talking about invisible forces, like the flow of air or the way heat moves around. Turns out this same idea of simulation works for that stuff too.
The magic tool for this is called computational fluid dynamics, or CFD for short. And honestly, the best way to get your head around it is to just think of it as a virtual wind tunnel that lives on a computer. Before this, if you wanted to test a new car design, you had to physically build a super expensive model and stick it in a real wind tunnel. Now, you can test hundreds of designs digitally. You can see how air and water flow. It literally makes the invisible visible.
So how does this actually play out in the real world? Let's take a problem from our list that sounds pretty simple. How do you improve the cooling in a greenhouse on a blazing hot day? You can't just guess where to put the fans and vents, right? If you get it wrong, all the crops could die.
The solution? You guessed it, you use CFD. Engineers create a digital twin of the greenhouse. They simulate the airflow and bam! They can instantly see where the dangerous hotspots are. And from there, they can try out tons of different layouts for the cooling pads and fans, all digitally, until they land on the absolute most efficient design.
And what's so cool is that this same powerful idea applies to so many different problems. We're talking about using this to figure out how to reduce pollutants from a reaction chamber, to design water jet nozzles that cut better, to improve how biowaste is incinerated, and even to analyze how heat affects food to make it last longer on the shelf. It's incredibly versatile.
Okay, so we've designed these amazing, super efficient parts, but there's a problem. How do you actually make them? A lot of these complex, organic shapes are basically impossible to create with old-school manufacturing. And that brings us to our next big topic, the new shape of manufacturing, building things in a digital world.
Yeah, we're talking about additive manufacturing, or what most of us just call 3D printing. The process is pretty revolutionary. Step 1, you design that super complex, optimized part digitally. Step 2, and this is the really important part, you simulate its performance before it even exists. You even simulate the printing process itself.
Then, and only then, step 3, you print the optimized part layer by perfect layer. And that simulation step is absolutely crucial. It helps prevent failed prints, which waste a ton of time and really expensive materials. Looking at our list, we see engineers doing exactly that, simulating the thermal performance of the 3D printer extruders, analyzing the whole fusion bed deposition process, and even testing the heat capacity of the plastics they use. It's all about making sure that digital blueprint turns into a perfect physical part.
All right, for our last big topic, we are scaling things up. I mean, way up. We're going from tiny, printed parts to massive ships. We're heading out to the high seas to look at naval engineering, a field where the stakes are incredibly high and where simulation is absolutely essential.
And just to give you an idea of how important this is, we found 23 distinct naval engineering projects on the list we looked at. 23. That's a huge chunk. And it just goes to show how critical this digital approach has become when you're dealing with something as complex as a giant ship.
And just look at the kinds of problems they're solving. These are serious life-or-death challenges. We're talking about using vibration analysis to make sure an engine or mast doesn't shake itself apart. They're running structural shock analysis for things like underwater explosions. They're modeling ship collisions. They're figuring out how a hull will handle the extreme twisting forces in a massive storm. They're even doing thermal analysis on LNG carriers to make sure the cargo stays safe. It's mind-bogglingly complex.
So, we've talked about lighter parts, invisible forces, brand new ways of manufacturing, and making massive ships safer. They all seem so different. So what's the common thread here? What's the one big idea that connects all of this? It's this: solving physical problems in a digital world. It's all about creating a digital twin of a real-world object or system. A perfect virtual copy that you can test, you can stress, you can even break, and then you can perfect it in the computer long before you spend a single dime building it for real.
You know, there's a great way to sum it all up. The ultimate goal is to use the digital world to predict and perfect the physical world before you ever build a thing. It's all about foresight. It's about using computers to ask what if 1,000,000 times over to find the absolute best design from the get-go.
And this all leads to a really fascinating final thought. This tech is getting more powerful and easier to access literally every single day. We're getting to a point where we can simulate almost anything with unbelievable accuracy. And so that leaves us with the biggest question of all. If we have a tool this powerful, a tool that can help us build a safer, stronger, and more efficient world, what problem should we solve next?